Gibbs Free Energy at non-standard conditions. As discussed, in some cases temperature affects spontaneity of a reaction and whether an equilibrium exists for a reaction. We won't go over this in great detail, we've done that in a previous topic, and if you'd like, go back and check it out. But a simple thing to remember is if delta H and delta S have opposite signs, then you can tell whether a reaction is yes or no, whether it's spontaneous or not. You don't need to worry about the temperature. It's only when the signs of these two variables are the same that there is a temperature dependence. Let's start working examples. Example 1, freezing water. Examine the impact of temperature on the freezing of water at 1 atmosphere pressure, where you have water in a liquid state goes to water in a solid state, or ice. Delta H for this process is equal to delta H of fusion. Its sign is negative since freezing requires energy to be removed from the water. Delta S is negative as the crystal has more water than the liquid water. Questions: does this process have an equilibrium? If there is an equilibrium temperature, will it become spontaneous above or below the equilibrium temperature? Answer on next slide. Does the process have an equilibrium? Since the signs of delta S and delta H are the same, the process will have an equilibrium. Okay, so will it become spontaneous above or below the equilibrium temperature? Well, we've got delta S is negative, therefore negative T delta S is positive. As T becomes smaller, delta G becomes more negative. As a result, the process will be spontaneous below the equilibrium temperature. Example 2, burning gasoline. Examine the combustion of gasoline, also known as octane, and that's right over here, C8H18, under standard conditions. First, what are the signs of delta H and delta S? 2, does the process have an equilibrium? And 3, if there is an equilibrium temperature, will it become spontaneous above or below the equilibrium temperature? What are the signs of delta H and delta S? Delta H, the change in enthalpy, is negative since combustion releases energy. Delta S, the change in entropy, is positive since the number of moles of gas increases. Does the process have an equilibrium? No, since the signs of delta H and delta S are negative and positive, this reaction will occur at any temperature. There is no equilibrium temperature. Example 3, photosynthesis. Carbon dioxide plus water yields oxygen plus glucose. What are the signs of delta H and delta S? Does it have an equilibrium? And if so, does it become spontaneous above or below the equilibrium temperature? What are the signs of delta H and delta S? Well, the change in enthalpy is positive since energy from the sun is required to drive the reaction. The change in entropy is negative since fewer moles of gas are generated. Right, we start with 6 moles there plus 6 moles of water gas, water vapor, that's 12. And on the other side, we have 6 moles of gas. We don't count the solid, so 12 is greater than 6. Does the process have an equilibrium? No, since the signs of delta H and delta S are positive and negative, this reaction will not occur spontaneously at any temperature. The reaction is unfavorable at all temperatures as both the enthalpy and entropy terms are positive. That's why plants need energy from the sun to grow. A continuous input of energy is needed for this reaction to occur. Let's dissolve ammonium chloride in water to form the ammonium ion and chlorine ion. Delta H is positive and delta S is positive. Does this process have an equilibrium? If there is an equilibrium temperature, will it become spontaneous above or below the equilibrium temperature? Does this process have an equilibrium? Yes. Since the signs are the same, there will be an equilibrium. Will the process become spontaneous above or below the equilibrium temperature? Above the equilibrium temperature, when the negative term, negative T delta S, is greater than the positive delta H term. Consider the combustion of carbon monoxide at 298 Kelvin. And here's our values for delta H and delta S. Does the reaction have an equilibrium? What is delta G system for this reaction at 298 K? If it has an equilibrium, at what temperature? If it has an equilibrium temperature, will it become spontaneous above or below that temperature? Does this reaction have an equilibrium? Yes, since the signs of delta H and delta S are the same. What is delta G for this reaction at 298 Kelvin? Well, here's our Gibbs equation here. We plug in the values for delta H, delta S, and then the temperature is 298. Carry out the math, and we get a delta G of minus 514.3 kilojoules. If it has an equilibrium, at what temperature? Well, we've already said it has equilibrium, so then it's just delta H over delta S, and the equilibrium temperature will be 3262 Kelvin. Will it become spontaneous above or below that temperature? The reaction will be spontaneous below 3262 K when the negative enthalpy term, right, and that's over here, is larger than the positive minus T delta S term. So let's just explain this. You see a negative here and say, wait a minute, why are you saying it's positive? Well, delta S is negative. So it's multiplied by a negative sign, you get positive. So that's why we say the entire term is positive. Example 6, decomposition of silver oxide. We have the equation here. Silver oxide decomposes into silver and oxygen. We have our values for delta H and delta S for the reaction. And does it have an equilibrium? What is delta G for this reaction at 298 Kelvin? If it has an equilibrium, at what temperature? If it has an equilibrium temperature, will it become spontaneous above or below that temperature? Does the reaction have an equilibrium? Yes, because the signs of delta H and delta S are the same. What is delta G? At 298 K, we have our equation. We plug in the delta H value, then we plug in the delta S value and the temperature. Again, that's always in Kelvin, and we've got the minus sign in the equation, and we get delta G is 22.6 kilojoules. If it has an equilibrium, at what temperature? We have our simple equation here. T equilibrium is delta H over delta S. Put in the numbers, and we get 468 K. Will it become spontaneous above or below that temperature? It will be spontaneous above 468 K. Why is that? The negative T delta S term, that's this thing right here, T is positive, delta S is positive, so the overall term is negative. So when that gets larger than the positive enthalpy term, delta G will be less than 0, and it will be spontaneous. Consider the following process. Solid water, ice, melts to form liquid water. We've got the values for delta H and delta S. So we find the equilibrium temperature by dividing delta H by delta S and getting 273 Kelvin. At this temperature, the reaction is in equilibrium. Small amounts in heat, addition or removal, will alter the direction of the process. Both delta H and delta S are positive. The ratio predicts that below this temperature, water will solidify to become ice, and indeed, this is the freezing point of water, 273 Kelvin, which is 0 degrees Celsius or 32 degrees Fahrenheit. How cool is that? On the previous slide, we said that ice would freeze at a temperature below 273 Kelvin or 0 degrees Celsius. Didn't really show you why, so we're going to show it to you right now. So at 20 degrees Celsius, let's find delta G. Okay, so it's delta H minus T delta S. The 20 degrees is a trick. You don't want to put that in here. You want to put the Kelvin temperature. And you find that delta G at 20 degrees Celsius is minus 556 joules per mole. Okay, so delta G is negative. When you're below the freezing point that we just said was 0 degrees Celsius or 273 Kelvin, you get a positive delta G. And we're using joules per mole here because there's just 1 mole of reactants. end products, right? We just have a 1 there and a 1 there. So now let's go to the next slide with these data. These values for delta G just above and below the freezing point of water do make physical sense. When you're at 20 degrees Celsius, above the melting point, we found that delta G was negative. So that means this reaction will go this way. At minus 20, delta G is positive, so water will go the other way. It will freeze. If we did the math for that, that's what we would find out. And at 273 Kelvin, the reaction is reversible and in equilibrium. Equilibrium means that at this temperature, substantial amounts of products and reactants coexist. There is no driving force in either direction, so you will have ice and water at the same temperature. And if you add delta S for the system to the surroundings, you get delta S universe is 0, which means it's a reversible reaction. We will now consider the vaporization of methanol as it goes from a liquid to a gas. Here's delta H and delta S. We want to find at what temperature is the reaction reversible, and then will vaporization become spontaneous above or below that temperature? At what temperature is the reaction reversible? We divide delta H by delta S and we get 336 K. At 336 K, delta G is 0 and the products and reactants coexist. This is the boiling point of methanol. Will vaporization become spontaneous above or below that temperature? Both terms are positive. So the reaction is spontaneous above 336 K. As T increases, this term here, negative T delta S, becomes more negative, which makes delta G more negative, and the reaction becomes more thermodynamically favorable.